Hello everyone, hope you are doing well. So this video which I had promised to do on discrete probability distributions was long overdue. So my apologies for that. I have been traveling and I could not do this on time. But as promised, I am going to record this particular thing and I share with you today. Now, I hope that this particular video that was on discrete probability distribution did not have any bearing on whatever you had learned from Professor Shiva regarding topics related to your normal distribution, sampling, hypothesis testing, and other things. And it is also not going to have a lot of bearing on what you are going to discuss, what we are going to discuss on topics related to regression tomorrow and the day after, right? However, because I had promised and this is part of this particular course, I'm going to record a video and I'm sure that this is going to be helpful for the future topics that you're going to discuss in this particular program across different subjects, right? So please pay attention. This is going to be useful for you. We will try not to ask questions which are directly pertinent to this particular video. Whatever we have covered in the class is what you will be tested on, but it is always better to go through this particular video in either case, right? So I advise all of you to go through this particular video. All right, without much ado, let me get into the discussion on this. Okay, let me share my screen for that. All right. So in the second session, we discussed about probability and probability distributions. We spent some time discussing about what is probability, and we discussed that the probability is the likelihood of occurrence of an event, and it is dependent upon favorable events and total events. So the technical formula for probability happens to be the ratio of total favorable events by the total number of events, right? And we discussed about that the probability value can take a minimum value of 0 and a maximum value of 1, right? Now, whenever the probability happens to be a special case that is equal to 0.5, then we can say that that event is equally likely to happen as it is equally unlikely to happen, right? Now, we could take a special example of something like the toss of a unbiased coin, where the occurrence of both head and tail are equally likely. Then we can say that the probability of occurrence of head is as likely to happen as it is unlikely to happen, or that it is likely that a tail would also occur, right? So that is generally what we can say about events where the probability happens to be 0.5, right? Now, one of the important things that is mentioned over here is the concept of sample space. Now, sample space is basically a representation of all possible outcomes that can happen for that. Now, sample space means that if there is, for example, let's take the case of rolling a die. Now, when you roll a particular die, you know that you are only going to get total 6 outcomes. They could be random. The occurrence of one of these events could be random. That is, you might get a 1 or a 4 or a 5 or a 2, but it has to be within 1 to 6. So that particular numbers that you mentioned over here happens to be the sample space, right? The same way, when you have a particular coin and you are tossing that particular coin, there are only 2 major occurrences that can happen. That is there is a head or a tail, right? Now, the same way, if you are depending upon the event that you're looking at, you can either purchase or not purchase. Or if we are going to have a class tomorrow, a particular student can either be present or absent, right? So there is no other possibility that could probably happen. So these occurrences that we are talking about, these possible outcomes that we are talking about, are basically what comprising of a sample space. Now, if a particular value that is there over here, like for example, take the case of rolling a die. We are saying that when you roll a die, you are only going to get numbers between 1 and 6, right? Now, when I'm saying this particular thing, if we are saying that what is the probability that you are going to get 1? Now, if you throw the dice enough number of times, there is a chance that you will definitely get 1 out of that. Now, that means that there is a negative probability that is there. That is, it might be 0, that you might have a dice which always gives you a 6, but there is a outside chance that you might still get 1 out of that, right? But if I ask you what is the probability that you will get 7, now 7 is not in the sample space, then the probability definitely has to be 0. So if you are talking about any kind of probability situation, if you are saying that what is the probability of an event which is not part of your sample space, automatically the answer for that is going to be 0, right? So that is the way you can look at this particular thing. Now, any experiment which involves these outcomes where there is a probabilistic chance that might be there of occurrence of any of these things, that kind of an experiment is what we call as a random experiment. Now, if I am saying something opposite to a random experiment, then there is a deterministic experiment. Now, a deterministic experiment is something like, if you are, let's say, for example, if you throw something in the air on the earth, right? And if it has enough weight, not something like helium or helium balloon or things like that, if it has enough weight, obviously with gravity, it has to come down. So it is a deterministic experiment. That means that you know for sure that there is only one outcome that can come. Whenever there are more than one outcomes that is possible, then that is called as a random experiment. Now, the occurrence of one of these random outcomes is what we refer to as a random variable. Now, random variables in general, when we are talking about random experiments, random variables can be of two types. One is a discrete random variable, the other one is a continuous random variable. Now, a discrete random variable is something that has a discrete number of occurrences within the sample space, right? It could be infinite values as well, but they are discrete in number. As opposed to that, in a continuous random variable, the occurrences that are there in the sample space are not discrete. They can be continuous. So that means that even within limited values which are there, there could be infinite occurrences between them. For example, if I'm talking about for a continuous random variable, if I randomly pick any particular weight of a packaged product, and I think that on the packaged product it says 1 kg, it is not necessarily going to be exactly 1 kg. It is only going to be based upon the accuracy of your measuring instrument that can measure what is the exact weight of it. Let's say your measuring instrument can measure the weight up to 10 decimals, right? So then you can have any value that could be 0.9999995 to maybe even 1.0000235. Right, so it could be any number like that. So there could be a number between these two. There are so many numbers which could be between these two, which could be the weight of that packaged product, which is what makes this continuous random variable have a lot of numbers in the sample space. As opposed to that, if you're talking about, let's say, number of grains of sugar in 1 kg, assuming that we have enough patience and we run this particular experiment, we can discretely say that you are going to have X number of grains. It is not going to be, let's say, 123.5 grains. It definitely has to be, even if it is not rounded, you can still count that as 1 grain, right? So there is a discrete number of grains which are going to be there. So that's the difference between a discrete random variable and a continuous random variable. Now, in general, the notation for a random variable that we generally talk about in mathematical notation, in probability, in statistics, is this particular letter, capital X. So whenever we talk about random variables, we talk about capital X, right? Now, usually when we talk about variables in mathematics, high school mathematics, we always talk about small x. But here, whenever we talk about random variable, we always use this particular letter, capital X, right? And this is a very important notation that you can even see in your textbook as well, right? In many of these textbooks, many statisticians generally use capital X to represent random variable, right? Now, why is this particular notation important? We will understand as we go forward. Now, having seen this particular thing, we also discussed about something called as discrete probability distribution, and probably we stopped at that particular point. But let me refresh your memory is over here. And what is this concept of probability distribution, and especially for discrete probability distribution, because we are talking about discrete random variables, right? Now, probability distribution is basically a distribution of all the values that can be taken, right? Imagine there is a random experiment, which is the toss of a coin, right? Toss of a coin. Now, we know that the sample space in this particular case includes two events, right? One is a head, the other one is a tail. And if assume that this is an unbiased coin, when I say unbiased coin, that means the probability of occurrence of head, which is generally written as P of X, which is my random variable, that it takes H value, is equivalent to probability that X will take P, which is my tail, is the same as 0.5. Right? Now, there are only two events which are there in this sample space, which is 0.5, and each having a probability of 0.5. If I represent this particular thing either in a table or on a graph, and I have two events, which is head and tail, and I am having on my y-axis values between 0 and 1, which is the probabilities, right? Now, if I am representing that, then that particular thing is what we call as a probability distribution. Now, we know here that both head and tail have an equal probability of how much? Is 0.5, right? So this particular thing that you see over here is what we refer to as our probability distribution, right? Now, in here we have two events, right? There could be many such occurrences that could be there. Now, if you look at what we see over here, in this particular case, in the example that is given over here, imagine there is an exam that is being conducted where the maximum marks happens to be 4, and this is an exam where there are no negative marks. The minimum marks that somebody can get is 0, and the maximum marks that somebody can get here is 4, right? Now, out of the total 200 students which are there, even if somebody is absent, then they can probably get a 0 out there. Then the total value that you are going to get over here happens to be one among these values, right? One among the values, which is 0, 1, 2, 3, 4. And you can see that there is a distribution of the number of people who have got these scores, which is mentioned over here. Now, the good part with such kind of data is that we know that relative frequencies, which we generally can calculate based upon the data given in such a format, is nothing but the same as the probabilities, right? Now, what we are seeing over here as probabilities is nothing but probability X is equal to certain X value, the capital X being the random variable, and X being a certain value that can be taken, which is 0, 1, 2, 3, or 4. So you can call this particular thing, which you see over here, as probability that X is equal to 0. Now, if I generally have to represent this as a graph, you can clearly see that if these values are between 0 and 200, we can say that 0 was having the maximum number of people, that is 80, right? Then you have 50 people having 1, 40 people having 2, 10 people having 3, and about 20 people getting 4, right? So this is how you can represent this particular graph, where these values are 0, 1, 2, 3, and 4, right? Now, if I have to convert the same, instead of this y-axis being frequencies, if I have to represent in terms of relative frequencies, that becomes my probability distribution, right? Now, you know how to calculate relative frequencies. It is just the value that you are getting by the total number of occurrences, which is 200 in this particular case. So you have these values. Now, the same thing will get translated into a probability distribution. The only thing that will change over here is that instead of the actual number of people having over here, as we represented in the case of head and tail, In the y-axis, you will only have 0 to 1 values, right? So 0 will be, as you can see from here, it will be 0.4. So this is 0.4. Then you will have 0.25 over here, 0.2 over here, let's say 0.5 over here, and 0.1 over here, which is very similar to this particular thing. Just that on the y-axis, you have your probabilities instead of the frequencies. So here you have frequencies, here you have probabilities. That is what you are seeing over here, right? Now, this is the case of discrete distribution. Why is this discrete? Because you can see that the random variable x is only taking values 0, 1, 2, 3, and 4. And you can see that there are gaps between the bars that I'm drawing over here. Now, if it was a continuous probability distribution, as you would have seen in normal distribution, there would have been values between 0 and 1, like something like 0.7 or 1.2 or 2.8. These values would have been there, and this graph would have been a continuous one, right? And that is the difference between a discrete probability distribution and a continuous probability distribution, right? Now, even if the discreteness is at this level, that let's say, for example, I can only calculate at 1 decimal, even that becomes a discrete probability distribution, right? So you should always look at how much discreteness is there. So for some of them, even for discrete probability distributions, we assume them to be similar to continuous distribution, right? Let's say the marks that could be scored are like 10,000, and you have values between 0 and 10,000. That is a huge number of values, right? So that's very close to being continuous. So you are saying that you can get values which are almost any value between 0 and 10,000, and hence it becomes closer to that. So this is something called as approximation. If you want to learn more about this, you can refer to the textbook. You can see that there are certain approximations where even discrete distributions are considered to be equal to continuous distributions, but that is not in the purview of this particular course, and that is something that you can learn if you are interested more about it. Now let's focus on the probability distributions, especially for discrete probability distributions, and then we focus on two main things among them. One is the binomial distribution, the other one being the Poisson distribution. Now, probability distribution, I have mentioned that the probability distribution is basically the distribution of different values for the different discrete values that you can take. Now, if I say, for example, let's go back to this example over here. So each of these values that you have over here in the sample space, you have probability of x is equal to h and x is equal to t. You can see that the probability of or x is equal to h plus x is equal to t would be equal to 1. Now, the same way, if I say that there is a particular sample space where the values that the random variable can take are x1, x2, and so on till xn, we can always say that the probability x is equal to x1 plus probability x is equal to x2 plus and so on, all the probabilities. When I sum this particular thing, what do you think the answer would be? The answer is nothing but 1. Why is that? The reason is because we are saying that the sum of all the probabilities that the random variable can take within the sample space has to be equal to 1. There is no other way that it can take any other value other than these things, right? Even if it is that all the values up till this particular thing could be 0, then xn, the probability that x takes xn has to be equal to 1, right? So that means that any kind of distribution can be there within this particular thing of values of the probabilities, but the sum of all these probabilities has to be equal to 1. Now, because this p of x is equal to x1 is a very, very cumbersome way of writing this, mathematicians said that let's represent this particular thing as f of x1, right? F of x1 or which is nothing but probability x is equal to x1 is basically a different way of representing this. And a generic f of x, basically, which is talking about the different probability values that can be taken by the random variable, and x representing all of these values x1 to xn, is what we refer to as the probability distribution function, right? Which is nothing but the shape of all of these different values that can be seen in this probability distribution graph, right? So that is basically represented over here. Now, the reason why we are interested in this probability distribution function is sometimes this particular probability distribution graph has a nice shape or nice pattern to it. Now, and that's an important way for us to understand that, oh, if there is a pattern to this particular thing, we can even, whenever there is a pattern to a particular graph, we know that we can always convert that into a mathematical formula. That makes it easier for us to calculate the probabilities in the future. For example, if I say that this is a particular line that is there, which is going through the origin, we can definitely say that this can be represented as y is equal to mx, right? That is the nature of that particular thing. And whenever the graph is like this particular thing, we can always say that it can be represented as y is equal to ax plus bx square, right? X being over here and y being over here, right? So like that, whenever there is a shape to this particular graph, we can always represent that using a mathematical function. That is the fundamental principles on which what we saw as coordinate geometry is built. Right? Whenever there is a shape, we can always represent it using some algebraic mathematical equation. Now that is what property that we are going to use. Now, this f of x is represented over here. As you can see, it says that f of x always has to be greater than or equal to 0. Now, what is the minimum value that the probability can take? It is 0. What is the maximum value it can take? It is 1. But it has to be, and it cannot be negative, right? And this particular symbol that you can see over here, this is sigma. Sigma is nothing but the sum of all values of f of x, right? That is f of x1 plus f of x2 plus f of x3 and so on, till f of xn, all the values which are there in sample space, the sum of all of that has to be equal to 1. This is nothing but what we have represented as p of x is equal to x1 plus p of x is equal to x2 and so on up till p of xn, x is equal to xn, which is there where x1 to xn are all the values which are there in the sample space. This has to be equal to 1. That is nothing but the same thing that is represented over here, right? Now, there is another important thing that comes in space over here whenever, and this is something that you will keep seeing more often in this particular program in other courses as well, is this concept of expected value. Now, expected value is very similar to something like your mean or an average value that we have discussed in the first session, right? Now, expected value is more closer to the weighted mean. Now, instead of the weights which we have seen in the weighted mean situation, here the weights happens to be the probabilities. So expected value over here is calculated as sigma being the sum of x into f of x. Now, if I say, let's go back to this example of what we saw over here, this particular thing, right? Now, if you look at this graph, let me take this particular thing into OneNote, and then probably we can use this. So we have, let's say, for example, x being 0, 1, 2, 3, and 4, and the frequency being in 80, right? 80, 50, 40, right? Yeah. 80, 50, 40, 10, and 20. Now we have correspondingly calculated. So if I ask you what is the weighted average of the score that people have got over here, you would have done a simple sum of, so for you to calculate the weighted mean, you would have done something like this. That is 80 into 0 plus 50 into 1 plus 40 into 2 plus 10 into 3 plus 20 into 4 divided by 80 plus 50 plus 40 plus 10 plus 20, and this would have given you the answer, right? The same way, you can also calculate this particular thing, which is now called as the expected value. Now, expected value, the formula that is given there is sigma, which is sum of x into f of x. What is f of x? F of x is nothing but our probabilities. Is what we represented as p of x is equal to x, right? So we said that this can be calculated as 80 divided by 200, 200 being the sum of all these values. 80 divided by 200, which gave us 0.4. 50 divided by 200, which gave us 0.25. 40 divided by 200, which gave us 0.2. 10 divided by 200, which gave us 0.05. And 20 divided by 200, which gave us 0.1. So this expected value, or expected value of the value that can be got by the students over here, can be calculated as 0.4 into 0 plus 0.25 into 1 plus 0.2 into 2 plus 0.05 into 3 plus 0.1 into 4. Now, if you calculate this, this happens to be 0.25 plus 0.4 plus 0.15 plus 0.4. So this is 0.65 plus 0.55. So 1.2, right? So what we can say is the average mark that people have got in this particular exam, or the expected value of marks that people would have got in this exam, is 1.2. Now you would get the same value over here as well. I've done that. Now, expected value, you can easily correspond that with the weighted mean, and which is what we have calculated over here, right? That's just that the formula represented over here is slightly different. So what is expected value? It is a weighted mean where the frequencies are replaced by the probabilities. So f of x is nothing but your probabilities. Okay. Now we said that whenever the probability distribution has a special shape, it is of importance to us, and that's what we are looking at, right? Now there are different kinds of discrete distributions which are of importance to us. Some of them are binomial distribution, multinomial distribution, Poisson distribution, and hypergeometric distribution. These are some of the famous discrete distributions. Now, out of that, there are two distributions which have a special place, and that's what we are going to discuss about. One is binomial distribution, the other one is a Poisson distribution. Now, what is this binomial distribution and Poisson distribution? Now, binomial distribution is that particular distribution where the sample space has only two events which can happen, and they can be equated to success and failure. Now, you can even say that head and tail can be success and failure, because if we are saying that we attribute tail to success, then head has to be failure, right? So like that, whenever there is any particular event where the sample space has two specific events, and that particular events are independent to each other, and the probability of that particular event to happen does not change from trial to trial, then such a type of event or experiment is what we refer to as a binomial experiment, right? And the distribution of the probabilities that we get with that particular thing is what we refer to as binomial distribution. Now, the only thing that you have to notice over here is that the sample space in this particular case has only two events. One is success and the other one is failure. Now, please note that it is not necessary that the probability x is equal to success has to be 0.5. It could be anything, right? It could be 0, it could be 0.1, it could be 0.5, it could be even 1, right? But the only thing is, we note that the probability of x is equal to failure. But what do we know about sigma f of x? We know that sigma f of x, which is nothing but probability of x is equal to x1 plus probability x of x is equal to x2. This is always equal to 1. That means the probability of x is equal to success plus the probability x is equal to failure always has to be equal to 1. That means probability of x is equal to failure is always equal to 1 minus probability of x is equal to success. Right? So that's what we are, that's how we calculate any of these things. So if your binomial distribution can be represented over a graph, and we are saying that this is success and this is failure. If I am saying that this is equal to 0.6, obviously this has to be equal to 0.4, right? And if I am saying that success is equal to 0.3, obviously this has to be equal to 0.7. Like that, this is how the distribution works. Now, we are not just interested in probability of one event to happen. Our interest is in probability of n such events to happen. Whenever there are n such incidents that happen, how do we know what is the probability? Like, for example, if I am tossing a coin 20 times, what is the probability that I'll get head thrice? That is of interest to me, right? Maybe that could be of interest to the captain of a cricket team. Whenever he wants to always, he or she is, let's say, for example, very superstitious and they only believe that tails is what they have to say. Now, if they want to assume that this is like a binomial experiment and they have seen the data of what, whenever you toss a coin, what you get, your probability is this much. If you want to bet on that particular thing, what is the probability going to be, right? Now, for that, you can actually look at this binomial probability. Now, remember that when I said that whenever there is a shape to a particular nice shape to a probability distribution graph, you can always represent that using a function. And that's what happened over here. So when people saw that this particular binomial distribution has a nice shape, then they started saying that, hey, why can't we probably put that in the form of a function? And that is what gave us this particular thing. Now, this particular function, while it might look ugly, is very, very convenient for us to solve, calculate, right? Now, when we do an example and when we try to solve this particular thing, you will have more understanding of what this is, right? Now, in this particular case, P represents the probability of success. Obviously, because P is probability of success, 1 minus P is the probability of failure, right? N represents the number of independent events that have happened. Let's say, for example, toss of a coin, if it happens 20 times, if we are saying that we are interested in calculating what is the probability that exactly 3 of them will be heads or tails, which could be defined as a success, how do we calculate the probability corresponding to that? Now, please always note that f of k is nothing but probability x is equal to k. If you have trouble remembering what f of k stands for, always you can write it like this so that you can understand that, right? Now, this formula can be used to calculate the value corresponding to that, and there are certain formula corresponding to expected value and variance which you can easily calculate based upon the number of events happening and the probability corresponding to that, right? Probability of success corresponding. So let's do one thing. Let's not fret about the formula over here. Let's try to solve this one of the questions, which will make it easier for you to understand this. So I'm taking this particular problem over here, and let's try to solve this. So I have a formula kept over here, so I'm going to use this whenever it is required. So let's see what this is saying. It says TCS is a large IT company which is facing a lot of resignations as they are asking people to come back to work from office. As if we choose any 3 candidates, now 3 is basically the number of, think of this equivalent to the number of toss coins. Now, when a person is asked to come back, there can be only 2 things that can happen. They can come back or they can resign, right? So there is the only 2 things that can happen. Assuming that all the negotiations and other things are kept aside, there are 2 things that can happen. One is that they can come or not, right? Now, if 3 candidates are called, what is the probability that only one of them will resign what is the probability that only one of them will resign, with the resignation probability being 0.1, right? Now here we are talking about, here we are saying that the probability of success, which I am representing to resignation probability, is given as 0.1, right? Now, what is the probability that they will not resign, which is 1 minus p? That would be not resigning probability, obviously would be 1 minus 0.1, that will be equal to 0.9, right? Now, what is that they are asking? And here, please note that if we choose any 3 candidates, that means n over here happens to be 3, okay? If we choose any 3 candidate, what is the probability that only one of them will resign, with the resignation probability being 0.1? Only one of them. That means what is that they are asking? Probability x is equal to 1, which is nothing but f of 1. That is, if we put that in this particular formula, it will be 3 factorial. What is factorial? Most of you would probably know this is nothing but, the 3 factorial is nothing but 3 into 2 into 1 and so on up till 1, right? 3 factorial by 3 factorial into minus 3 minus 1 factorial, right? Into p is 0.1 to the power of k. K is what? 1 into 0.9 into 0.9 to the power of n minus k. N is what? 3 and k is, okay, let me put it over here. N is 3 and k is equal to 1, right? So 3 minus 1, right? So what is this going to be? Let's look at it. This is 3 factorial get cancelled. This is 1 divided by, this is, so this is a mistake. Let me, there's just 1 factorial, right? 1 factorial. So this is 3 into 2 into 1 divided by 1 into 2 factorial. So that is 2 into 1. These two get cancelled. So this is into 0.1. And this is 0.9 square. So this is 0.9 into 0.9. So this happens to be 3 into 0.1 into 0.81. Right. So what is this? This happens to be 0.243. Now this is the solution for this answer. So let's try to put this over here. Let me calculate this. We can even calculate this particular thing. So I'm putting these values over here. N we found out to be equal to 3 and k happens to be 1, right? And what is p? P happens to be 0.1. Okay. So let's calculate this. So f of k is what we are calculating, which is nothing but n factorial. So factorial formula in Excel is fact n divided by fact 1 again divided by fact n minus k, right? This is multiplied by p power k 0.1 to the power of k into 1 minus p to the power of n minus k. N minus k. What did we get? Voila, we got the same value that we have calculated over here. So this is the one. So if you think that the calculation happened fast, just go back and revisit one more time whatever I have done. You can drag back the video and then slowly see this particular thing. Okay. Now, if some of you think that this is a very big formula and will take a lot of time and this unnecessary thing, I can even do that in Excel in a slightly better manner, right? Because these are famous distributions, Excel has already built in this particular thing into this formula, right? Now, how do I do that? So I need to type is equal to BINOM. So it is saying I'm giving you individual term binomial distribution probability. So select this binomial distribution, binom.dist, and it is asking the number of successes. So number S the number of successes, which is nothing but K, right? How many trials have happened, right? How many trials have happened? 3 trials have happened. What is the probability of success? Probability of success is 0.1, and it is asking whether it is cumulative or not. No, it is not cumulative for us. I'll tell you what is cumulative in the next problem, right? So let's say it is not cumulative and we have selected false. Let's see whether the answer matches. Yes, it exactly matches. So all you have to do is identify these 3 things and then put it in this particular formula where the first one happens to be K, number of successes, that is K, number of successes being for us, number of people will resign, right? Then you have number of trials, that is 3, total number of people who we have chosen, the probability of success, which is 0.1, and then just put it as false, which is not cumulative. That's all that will give you the answer. Now, this is how you calculate the probability distribution, right? Now, by the same logic, you can also calculate this particular thing. Now, I am not going to do the first solution for it. You can figure out how do you do the first solution. Maybe I'll write it over here. You can try to solve this particular thing in the first place over here. But let me show you the second solution, right? Now, what is that is given over here? Let's write down whatever is given in this particular case. A survey found out that 0.65% of all financial customers were satisfied. Obviously, again, taking these two as 2 events, one is two things that can happen. One is satisfied or not satisfied, right? So here, let me put it as P is equal to 0.65 as my success, right? Probability that it is success. Suppose that 25 financial consumers were sampled. That means these are the number of trials that are happening. So N is equal to 25. Now, what is the probability that exactly 19 were satisfied with the primary financial institution? So here, at least in the first problem, K is equal to 90. So you can calculate this simply, very easily you can calculate this. So how do you do that? You have P, you have N, you have K, and merely substitute this particular thing. All that they are asking is f of 90, right? So you can calculate that. Different ways. You know, first solution directly substituting this, or you can use binom.dist function, and that also gives you an answer. So I'm not going into this. Let me show you the answer to the second one. You can try this out. If you have a problem, I will help you with the solution later. Let's look at the second one. What is the probability that more than 2 consumers were satisfied that over here? This question is slightly different. Look at the sentence that is being given. It is asking more than 2 consumers. More than 2 consumers means what? The probability that X is greater than or equal to 2, right? That means probability or probability that X is greater than 2 rather, right? Just X is greater than 2. What does this mean? It could be probability X is equal to 3, probability X is equal to 4, and so on up till 25, right? So we are looking at whether 3 customers were satisfied, 4 customers were satisfied, or all the way 25 customers were satisfied. Now, this is a very time consuming thing, right? Now, this is where your cumulative distribution can come into picture. So you can look at this particular thing in 2 different ways. One, we are being asked what is the probability X is greater than 2, right? Which is nothing but f of 3 plus f of 4 all the way up till f of 25, which is a time consuming thing. But I know for a fact that sigma f of X is what? It is 1. That means f of 0 plus f of 1 plus f of 2 plus all these items which are there over here, this is equal to 1. There could be 0 customers which are satisfied, 1 or 2 customers which could be satisfied, or all the way 25 customers are satisfied. But I know that this is all equal to 1. So that means what? So if I have to calculate this value, let me put this as some maybe z, right? So if I have to calculate z, this is nothing but 1 minus f of 0 minus f of 1 minus f of 2, right? So that's all that I need to look at. So what we need to look at is we need to calculate either f of 0, f of 1, f of 2 separately and then calculate this, or we can also look at something called as cumulative distribution. So this is nothing but z is equal to 1 minus sigma f of 2, right? That is f of 0 plus f of 1 plus f of 2 up to that particular point. So we can use that particular thing to calculate. So let's use this, right? So here for the b part, I'm going to use the functions to calculate this. So I'm writing this n is equal to, put it over here. Know that n is equal to 25. K is, in this particular case, that is B case. A case, I'm not doing it, 2, and P is 0.65, right? What I'll do is, first I'll calculate. So what is of interest to me is P of x greater than 2, right? That is nothing but equal to 1 minus binom dot dist. What is the number of successes that we are talking about? 2 out of number of trials that are being done is 25. What is the probability of success is 0.65. In this particular case, please remember that I'm going to use cumulative, not non-cumulative, right? So in the previous example, you used false. Here I'm using true. Set. It is giving 1. Why is it 1? The reason why it is equal to 1 is because the probability of success of f of 0, f of 1, and f of 2 is very, very small. In fact, maybe if I just increase this, you can see that it is very, very small, 0.9999958. Means that the probability of f of 0, f of 1, and f of 2 is very, very small, and that's the reason why you got this. I hope you understand how you solve these kind of problems now, right? Now, let me give you an example of the Poisson distribution, and then we can solve some of the problems similar to that. So this is binomial distribution, right? Binomial distribution is always about successes and failures. Okay. Okay, so this is regarding the concept of your binomial distribution, right? So binomial distribution, we talked about successes and failures. Now let's look at the Poisson distribution, which is equally interesting. Okay. Now Poisson distribution or Poisson random variable is where we are looking at occurrences over a specified interval of time, right? Now whenever there are arrivals or occurrences of something, then that is where we usually look at Poisson distribution. Like we have successes and failures in binomial distribution, here we are looking at the number of occurrences in a specified period of time. Now, these occurrences could be anything, right? So for example, if you are talking about number of arrivals in a bank in a specified amount of time, or number of phone calls in a call center in a particular day, or number of defects in a manufacturing lot in a particular batch. So these are all different occurrences. Now these occurrences are very, very important. And if you look at and historically, when people looked at the occurrences of different events in a specific period of time or space, they found out that they followed this concept of Poisson distribution. Now, there are certain assumptions as similar to what we have done for binomial distribution, that we thought that all of these are independent events. Same way, we have certain assumptions in Poisson distribution as well. We say that when the probability of occurrence is the same for any two intervals of equal length. That means that if we are saying that the probability of occurrence is of a particular event is 0.5, in a particular time of 3 minutes, then we can say that in the next 3 minutes also the probability of occurrence is 0.5, something like that, right? So that is what we are talking about. And these, again, there is independence of the different events that are happening. So that is very important assumption, which is going to be there for other things that we are talking about. In general, the independence is a slightly very strong assumption that we make. It might not be applicable in many cases because the number of people who are occurring could be dependent upon the previous number of people. People might see how many people are getting into a line and then they decide or not decide to enter it. So that might impact the way we calculate things, but that's for an advanced level, right? To start with, we can always assume that there is independence. Now, Poisson distribution, very similar to how I talked about in binomial distribution. I said that there, when people saw that the probability distribution has a nice graph, they found out that we can convert that into a mathematical function. The same way, we found out that when we calculate this probability function for different values of what the Poisson function can take, that can also be nicely represented as a probable, nice algebraic equation, and that is what we are seeing over here. Now, note that unlike in your binomial distribution, where we had number of trials and the number of occurrences over here, the successes and failures, all those things, here we just have the average number of occurrences and the number of occurrences in a specified interval, which we are looking for, which we take as it only two inputs into this function. Now, again, the same way we said, if the function might be too difficult to comprehend, when we look at the formula, when we look at the problem, it might be easier for us to understand that. So let's get into trying to solve the problem, and that might actually help us understand this better. Okay, so let's get into that. So the Poisson distribution formula, let's look at this particular thing. So the question that is being asked over here is that cars arrive at the toll gate of Rameshwaram Highway at an average rate of 20 per hour, right? Now, if you see over here, lambda, which is this Greek symbol that is there over here, is representing the mean number of occurrences. Mean or average is the same. So as per the data that is given to us, lambda is given as 20 per hour, right? That is what is given. Now, what we are saying is, the question that is asked is, what is the probability that there are 12 arrivals in 30 minutes on a weekday afternoon? Now, please note that here the lambda is given in per hour, and the question is about what is the probability of 12 arrivals in 30 minutes, which is nothing but k, the number of occurrences in an interval, right? Always remember, occurrences in an interval, whenever you see that, nobody needs to tell you that it is Poisson distribution problem. You need to understand that on your own. So let's say k is equal to 12 per 30 minutes is what they are asking. And they are also asking what is f of k, which is nothing but what is the probability that x is equal to 12 given 30 minutes, right? That is what they are calculating. Now, please see that there is a difference between what lambda is and what k is. K is in 12 per 30 minutes and lambda is 20 per hour. Now, in such kind of problems, always convert your lambda in terms of what your k is in. Now, why am I saying this? This is based upon that assumption that we have made. We said that whenever there is a probability of occurrence for a particular event in a specified time, when you take the same amount of time the next time also, the occurrence will be the same. So that means that if we are seeing 20 people have come in 1 hour, by the probability assumption that the probability will be the same at same time intervals, this should mean that if I take a 30-minute interval, there should be 10 people who will be coming, right? How did I do that? I assume that there are two equal intervals of 30 minutes and I divided that 20 into 10 and 10. That is why we said that the probabilities are same. So that means now my lambda is 10 per 30 minutes and k is 12 per 30 minutes. Now I can lose this 30 minutes, which is not of interest to us, and I can simply represent lambda is equal to 10 and k is equal to 12. This is the only two information that is required for me to solve this particular problem. So let's substitute this particular thing. So f of 12 would be nothing but lambda power k, so that is 10 power 12 into e, which is e value is given over here, e power minus 12, sorry, minus 10 divided by k factorial, which is 12 factorial, right? So this is what 12 factorial we can calculate over here. So it's difficult for me to calculate this, so let me just use Excel to solve that. Right? So let me put the values first over here. Lambda is nothing but so let me put it is 2 per 20 per hour. It is nothing but this divided by 2 per 30 minutes. And I know that k is much 12 per same 30 minutes, right? So what I'm calculating over here is f of k, which is equivalent to this particular thing, right? So let's substitute this lambda power k. Lambda is 10 power k into what is that they're asking? E power minus lambda. E is, I can either use 2.71828 or Excel has a function exponential, which is nothing but e raised to power of minus 12, right? Or minus 10, sorry, minus 10 lambda divided by factorial of real of is that we are getting 0.09478. When we are saying that 10 people are coming in, they're asking 10 in 30 minutes, what is the probability that 12 will come? So you can see that average is 10, but the moment we are increasing it to 12, the probability is actually falling down, right? Now, please note that average does not always mean does. Sorry for the disturbance there. Here, please note that just because it is average, it does not mean that the probability will be 0.5, right? We can just check that because here it is 10 and we are saying that if what is the probability that 10 people will come, can always calculate f of k, right? So we are saying that if, okay, let's look at the formula which is given by Excel and we can substitute it there for us to understand that. Now, how do I calculate this again based upon the distribution, Poisson distribution formula, which is given in Excel? I can use Poisson distribution, similar to binomial distribution, and use Poisson distribution formula. What is x? X is nothing but k. Then what is mean? Mean is my 10. And what is cumulative? No, we are not looking at cumulative. So let's look at this. Are we getting the same answer? Yes, we are getting the same answer. Now, if I want to understand what is the probability corresponding to the average value, which is the same as a lambda, so I can just try to see how much is f of 10, right? Which is, or f of lambda, you want to see, right? Now, f of lambda happens to be Poisson distribution is 10, comma 10 again, and cumulative, no, not cumulative. You can say that the probability is 0.125. And the only thing that you will see over here is that for any other value other than 10, the probability value will be lower than that. You want to check that? Let's look at that. Let's say, for example, we take value of 9, right? So instead of 10, let me put this particular value as 9. Right? It's exactly the same, very close. So that's why you are seeing that. Put 8. It has come down, right? Or let me put it as 11. It is less than 125, right? Now, why am I saying this? The reason I'm saying this particular thing is because if I say Poisson distribution, I'll show you why I'm saying that, right? And you will be able to understand that particular thing. So Poisson distribution, the way this graph works is that look at this, the lambda value, right? So the distribution graph, which you will have for different values of lambda, the maximum value that you can take over here is at the value that is at lambda. That is the reason why the average value, and that's the reason why I said when you take those values on the left or the right of that lambda, you will get a value which is equal to or less than that always. This is the particular property of that Poisson distribution. Okay. All right. Now let's look at another formula for us to understand this particular thing. Okay. So you can play around with that formula for you to understand this. What is this question? SBI Bank at NIT Trichy has an average random arrival of 3.2 customers every 4 minutes. So what is that? That is lambda that is given to us. Lambda is given as 3.2 every 4 minutes, right? Next, what is the probability of having 20 customers in a 8? So K is given as 20 customers in more than 20 customers. That is greater than 20 in 8-minute interval, right? Now, what did we say? Whenever we have such kind of situations, we always convert lambda to be in the same thing as the K, like we did in the previous case. So because this is every 4 minutes, and we said that the probability will be the same every equal number of minutes. So 4 into 2 is 8. So every 8 minutes, it would be nothing but, this will not be nothing but 6.4, right? Now, what is that? So look at the lambda. Lambda is 6.4, and they are saying what is the probability that of having 20 customers in a 8-minute interval. That is very, very unlikely to happen because average number is only 6.4, and we are asking what is the probability of 20. Now, this is almost going to be equal to 0. Now, why am I saying this particular thing? You will see very clearly that this is nothing but the same way that we have calculated in the previous case. The question is about so probability x being greater than 20. This is nothing but probability x is equal to 21 plus probability x is equal to 22 and so on, which is nothing but 1 minus, it could be infinite number of people as well, but that is not of importance to us. It is nothing but the probability of f of 20 or sigma f of 20, or it can be nothing but 1 minus probability of x is equal to 0 minus probability of x is equal to 1 and so on up to minus probability x is equal to 20. The good part is this particular thing can be easily calculated from our Poisson dot distribution function using the cumulative form, right? So let's do that. Now my hunch is that the answer will be almost equivalent to 0. So we are calculating probability x greater than 20. Let's calculate that. This is 1 minus Poisson dot distribution. What is x over here? X is 20. What is mean? 6.4. Are we calculating cumulative? Yes, we are calculating cumulative. So 3.875 into 10 to the power of minus 6. That is almost close to 0. And that's what we are seeing over here. So this is, my friends, all about the discrete distributions. There are other discrete distributions that I mentioned in the when I was discussing about the types of distribution, hypergeometric and multinomial distribution. Some of that is given in the textbook. You can go through that. If you have more doubts, if you are interested to learn more, please reach out to me and we can discuss further. Now, in the next class, that is tomorrow's class, we'll be going to discuss about a very interesting topic and kind of foundation for most of the things that you're going to discuss in this particular program, which is called as regression, which is a very, very foundational thing. We'll discuss about that. Okay, if you have any doubts on whatever is mentioned in this particular video, please reach out to me and I'll be more than happy to help you. Thank you. And my sincere apologies once again for not doing this in time, but I was not able to do that because I had constraints on accessing the computer and internet. I'm really sorry for that.